All right. So I want to start with what you guys did on one of the questions on your quiz on Wednesday. So let's see. A truss like this. Okay, so let's first look at it. It is a truss because all of the forces are applied at the end, right? So that, and every member is pinned at the end only. So that makes it, every member of this truss is a two-force member. So yes, it is a truss. But let's see, let's use method of joints. Okay. And find forces in AF and AB. So which joint would you pick to find forces in member AB and AF? Okay, I'm gonna start calling names, okay? Let's see. All right, so let's see. If you have a camera, go ahead and turn it on. All right. So let's see. Who's the lucky winner?
Couldn't you just use joint A?
Okay, joint A.
Because and there's only
Right.
one Y one and one X one.
Okay,
And then
great.
since it has to be in equilibrium, it would be both would be 0 then.
Okay, so Brett saved everyone. So from now on, if I don't hear participation from everyone, I hear usually from 3 to 4 people. I'm gonna start calling names, okay? So yes, we'll start with joint A. Brett kind of explained all the way to the end of it, but I'm gonna take it a little bit slower. So joint A, we do FBD of A, so we isolate and draw the outline. We put active forces on there. I don't see any active forces. Then we put reactive forces. Reactive forces are going to be along the members. I see one going FAB, and then I go seeing FAF. Okay. I don't see anything else. So I have two equations to work with. Summation of forces in x direction equals 0. Anything that goes to the right is going to be 0. The only force I have is FAB, which is going to be 0. Summation of forces in y equals 0. Anything that points up is going to be 0. FA, F equals 0. So these two are going to be 0. Let's see. Next, let's find forces in members DC and DE using method of joint. So which joint would you pick this time? FBD of which one would you pick?
Joint D.
Joint D. Okay, that's the smart decision, right? So free body diagram of joint D. I'm going to draw, outline, isolate. Then active forces, I don't see any active forces on joint D. I see two reactive forces along the two members. It's going to be F, D, E. And these are unknown, so I'm just going to always draw them in compression. And F, D, C. Okay. Let's see. I'm going to take this one as x-axis, take this one as y. I can rotate my axis whichever I want, okay? So now let's see, summation of forces in y. equals 0. Y being this way. This angle is theta. Okay. So all I have is FDC. Is it going to be sine or cosine?
Sine, because
Sine
you're
theta equals 0. So FDC equals 0. Okay. Summation of forces in X equals 0. Anything that goes this way, I'm going to take positive. Okay. So I have FDE, and that's it. This is 0 too. Okay. So just we'll get back to this. Let's look at this problem. First, let's figure out if it's a truss or it's a frame. It looks like a truss. Every force that I see, which only force P, is applied at the end, at the joint. There is no member pinned in the middle, so they're all pinned at the end. So it is a truss. So let's see. If I draw free body diagram of joint C or D, let's pick D. Free body diagram of D, joint D. I'm gonna have isolate D, active forces, which I don't see any, and then reactive forces. I see DA going this way, DC going this way, DE going this way. Okay. Oh, I thought I closed all of my emails. Okay, let me see. All right. So again, I'm gonna rotate my X and Y. So let's take this one as Y. Like this, take this one as X. Summation of forces in X direction being 0. Anything that goes this way is going to be positive. FDA is the only one, so that's going to be 0. Okay. So that one is 0. So in some or a lot of trusses, we might encounter members that the forces in those members are 0. And we call those 0 force members. Okay. When a member is not carrying any load for me, and if it's not doing any work for me, what does that mean?
It's useless. It's a backup.
It's yeah, I wouldn't call it useless, but yes.
It's either used for construction or as a backup.
Exactly. So it is not doing any work for me. That means I can remove it. Okay. So my truss is going to be, oh, sorry. I can remove those two as well. So my truss is going to be like this. These two trusses are exactly the same as far as loading is concerned. Okay, so you see, although there is a force that is applied at pin C, but this member DC is not carrying any of that load at all. So I can just remove them. And as some people said, that was my next question. Why do we have them? The answer is it's for backup. In case something changes, in case something hit this point D and applies a force of P2, whatever that might be, then that is not a 0 force member. Then the truss can save its integrity. The other thing is for support, which some people said, it's during the construction. You might need to weld or pin some member in order to construct your truss, but then after your truss is constructed, then those are not carrying any load. Same thing here. If you draw free body diagram of joint C, this is going to be 0 too. So your truss is going to be pretty much like this. Again, these two are totally equivalent and similar as far as loading goes. And this is still a truss. It's 3 members pinned together. and the loads are only at the end. Okay, so here's something. In the problems I've asked you to find zero force member, you have to draw a free body diagram of joints to figure it out. So don't ever try to guess. Okay, that's the first thing. But here's a good indication for you. If you look at these joints, what you see is usually there are two members that are in line with each other and a third member with an angle going off of those two. See that? It doesn't have to be 90 degrees. It can be with any angle. That usually is a good indication that this one is a zero force member. Okay, so that's a good indication. But again, I don't want you to guess when you see a problem. It's a good thing that you look for them and says, hey, I guess D is a zero force member, but you have to draw free body diagram for it. Okay, so let me show you something when we say support. Okay, this was a tower crane. This is a similar one. It's not the exact one. And an accident happened, and you can kind of see it totally crumbled down. So there were two. There was a mobile crane. There was a tower crane, and the mobile crane, when it was moving around, it was a miscommunication between the two, drivers. One said turn right, he thought it said left, and so on. So the boom collided with each other, and this one totally crumbled down like a piece of paper, So zero force members can come and help in a situation like this, which obviously the force here and the impact and the load changing was too much that the zero force member couldn't take it either, and they failed. So this is a site that I was working, when I was working before doing grad school. But this is something happened. So you can see these structures are efficient, are light, they can carry a lot of load, but when the loading is changed and they're not designed for it, you can see something like a catastrophic can happen. Another thing that I wanted to share with you guys, I don't know, you might have seen this a lot all over the place, but videos such as this one. Okay, or here's another one. Okay, here's another one. Let me see. Here, I like this. I like this one. Okay, so have you guys seen these structures around? Here's another one. On Instagram and stuff like that, TikTok. So who can explain what is happening here? What are these called, or what is this happening?
Pretty much what's happening is the cable in the middle is actually holding the whole thing together. It's holding it up, while the three on the outside are actually more like support cables, keeping it from tilting one specific way and like tipping over. Exactly.
So in the statics, we learn about members, right? Thin members pinned together, which is kind of like this one. If you assume that instead of a nail going through wood, it's like a pin. Pretty much it can move, right? And we've been talking about ropes and stuff like that from the beginning of this course, and we always say ropes can only take tension, remember? So all of these ropes that you're seeing here, they're all in tension. So they all have a force that's pulling on them. And as it was said correctly, the middle cable is pretty much holding the entire structure. It's on its in tension and is holding the structure. Okay. And the other members, the wood members, are all in compression. But that's a very good example of what you're learning in this course, members in tension and compression and how they can support loads. This is known as tensegrity. Okay, so it comes from integrity and tensile or tension. So it's tensegrity. So how many of you have used tensegrity before? How many people have used tensegrity before? Not that you've seen it, right? A lot of you might have seen this, but how many of you have actually used it? Anybody? Colton, have you used it?
Yes, with some rigging for cranes, I guess.
Okay, well, it's way simpler than that.
Well, I know that, but
No, I mean,
used
you've used it in a much simpler way. That's what I mean.
yes.
So where have you used it? Do you know? All of you guys are using it right now. Everybody is carrying a tensegrity structure with them at all time. Okay, let me find it. Human body is a tensegrity structure. Okay, so your bone structure are what keeps your body in compression, or not your body. Bone structure takes compression. All your muscles and tendons are going to provide tensile load. So yeah, so that's gone. But anyways, your body, human body, is the best example of tensegrity. So if you search the word tensegrity on internet or TikTok or Google, Instagram, you're going to see a lot of like doctors and physiotherapists and all of that explaining human muscle, skeleton, and stuff like that. So it's another application of engineering in human body, which I think is pretty interesting. Okay, any questions about zero force members or tensegrity and stuff like that? Okay, do a little bit of research on it. It's pretty cool. You're gonna find a lot of creative stuff. All right, let's get back to boring stuff. Okay, so we're talking about frames and machines, and today I'm also gonna do some examples on frames and machine for you. We said every time that you see a structure is not made out of two force members or only two force member, it is a frame or it's a machine. Okay. First of all, I say frames and machines a lot. What's the difference between frames and a machine? I know we analyze them the same, but there's a difference between those two. What is a frame? What's a machine? Or do you call this tool a frame, or do you call this a machine?
It'd be a machine because aren't frames like fixed in place or whatever?
Yes. So the answer is yes, that's right. So frames usually are for supporting loads. Okay. They're usually fixed. Machines transfer load and usually try to help us, right? We're going to see, so the point of using a tool like this is to transfer load and help us, right? So without solving this problem, so this problem says find the forces at A, right? Without solving this problem, should the force at A be more than 5 or should be less than 5?
More than 5.
Should be more than 5, right? So this tool is supposed to help us, supposed to increase our force, our load that we are applying. So if you solve this problem and get force at A being 3.5, you've done probably some errors down the road, so you got to go back and check. So that's the purpose of machines. But as far as the statics and we are concerned, we analyze these two the same way. And the way we analyze them is that we take them apart, right? So I did the free body diagram for this one. It was a little bit quick, so we're going to do it again today. So the first thing I do is I'm going to take this apart. It doesn't have to be beautiful. As long as you know what is what, that is all we want. There we go, and there's one here. Okay, I just took all of the 5 members or 4 members apart. Then I would usually like to go back and put the labels and pins back on so I can keep track of what points they go together. Okay, then I have a C that goes here. Then I have an E, which is kind of the same line as C. And then I have another E here. I have my B here. I have my A here. Okay. So that's the step 1 of the free body diagram. Step 2 is put active forces and reactive forces, but we're going to do one by one while keeping an eye on where the pins are going to go together. And the reason for that is, as I explained last time, if I want to have a force on this one, because this is a 2-force member, let's call it FCD. Then I know that, hey, point C is going to have FCD, point D is going to have FCD. Okay. So FCD can be either tension or compression. If you want to flip all of those forces, that's totally fine. But the wrong would be if you draw it like this. Okay. Because then if you want to put it back, you can't have FCD going this way because this member is a 2-force member. The only way it can have a force is if its line, they share the same line of action, which should usually go through the pins. Okay, so when drawing the free body diagram of the members that are 2-force and 3-force and multi-force that they go together, you got to be mindful of that. I think that's the only thing at this point for this member that we had to worry about. Active force, I don't forget that, 5 pounds. B is a pin. I just put a BX and BY on it. You don't need to worry about the direction the first time you put it on there. Okay. For the second one, you got to be mindful because that one has to be opposite of this now. Okay. I don't want to miss the one at point A. Let's call it normal A. Okay. Let's move on to BEA. BX and BY, I have it. Let's have EY and EX. As soon as I draw that, I draw the opposite on pin E. So it's going to be EY and EX. And A, I don't want to forget an A. So this is done. This is done. This is done. Let's check, make sure that the bottom handle, lower handle is done too. EX, C, the only thing missing is the 5 pounds. Okay. So now when drawing free body diagrams of frames, it takes a lot of skills, right? You got to consider everything that you've learned up to this point. 3 multi-force members, rigid bodies, you know, which are all of these are rigid bodies, and 2-force members, and also how the similar pins, same pins, when they go back together, they should cancel each other out. So if I put this whole thing back together, every force that I drew on there should cancel each other out except these 2 that were already there. Okay. Questions about the free body diagram of a frame such as this one or a machine? Okay, so to solve this problem, what the problem is asking me is this NA. Okay, so I got to use one of these free body diagrams to solve it. And you got to always look to see, you can have up to 3 unknowns on every free body diagram, right? Because you have three equations: summation of forces in x equals 0, y equals 0, summation of moment. For each of those, you can use that, except this one. This one, the moment really doesn't make sense. For this problem, I'm going to pick these two. So I'm going to pick this one. And I have 1, 2, 3, 4, 5 unknowns. Okay. That really doesn't work out. So I'm going to use another additional free body diagram to maybe get 2 of these forces and then go back to solve it. So here I'm going to redraw them a little bit better now. Just those 2. I'm going to draw so I'm going to go based on my solution. So if I am putting the direction opposite of what I had before, I apologize. But let's go with this because my whole solution is based on these directions. EY, and then I have a BX.
In chat, they're asking if there's any certain way to pick out the 2, or
No, so the only way you can know is you always start with the force that you want, right? So in this problem, it says find NA. So I know that I have to use this free body diagram for sure, okay? But then when I look at this free body diagram, I see that I have too many unknowns, right? I have 1, 2, 3, 4, 5 unknowns right now. I can't solve it. So I gotta go look for another free body diagram. In this case, you can pick any other to find maybe some of the unknowns from the other free body diagram and get back here. Because look, if I use this one, I have 3 unknowns, right? That means I can solve it. I can find FCD, EY, EX. Then I can come back to this free body diagram and then I have 3 unknowns and solve it. So the golden number for you guys is 3 unknowns. That's you can do. And if you see a free body diagram that has more than that, you got to go use another free body diagram to find some of the unknowns. Okay. BX. Let's do BY and NA. This is my one of the free body diagrams. And then I said I'm using the lower handle. Okay. The important is that EX needs to be opposite. EY needs to be opposite of the other one. The C, I use the same. Yeah, FCD. And I have a 5. Okay. A little bit cleaner free body diagrams here. So it's this one and it's this one. Okay, so as I said, I'll start with the number 1 free body diagram. So from FBD1, I'm going to take moment about point E. Is there a better way to do it? If I take moment about point E, I can find FCD and then find EX and EY. Yeah, I need EX. Okay, yeah, let's do that. Let's moment, summation of moment about point E being 0. Anything that rotates this way is going to be positive. The distances that we have is, this is 1 inch. This is 3 inches. Okay. So summation of moments. So the 5 pound multiplied by 4 inches, and that's a plus, minus FCD. What is this FCD? What is this component? The vertical component. So you got to look for the triangle, right? This is 3. This is 1.75, isn't it?
It's one.
1.75. So it's going to be 1.75 over
Oh, yeah.
plus 3, whatever that is. Okay. Okay. So this will give you FCD of 39.693 pounds. Okay, the next thing I can do is write summation of forces in x equals 0. Anything that goes to the right, I'm going to take plus. So it's going to be EX minus 39,693. This time it's going to be 3 over 1.75. 3. This is pounds. It's going to be 0. EX is going to be 34,286 pounds. And you can do summation of forces in Fy and find EY, which I don't care, and you're going to see why not. Questions about this one? So again, what we are using here is from chapter 5. We're back to chapter 5, rigid body diagrams and equations. Okay, now my EX is 34,286. I can find EY also, but I don't even have to. You're going to see why not. In this, I can just write one equation and find my NA. What equation would you write? You have 3 to pick from. Summation of forces, X, summation of forces in Y, summation of moment. All you need is one equation and you can find your NA.
Summation of moment.
Okay, about what point would you pick it?
Point B.
Point B, why? Why did you pick B?
That gets rid of BY and BX. You're left with
Exactly.
NA.
And
then-
EY. See that? Also EY. So if, again, you can use any equations. You are able to solve this, but you want to just be efficient, right? And smart about it. So if you take summation of moment about point B equal to 0, EY goes through it, so I don't have to worry about this one. BX and BY, they go through it. I don't have to worry about it. All I have is EX that I already know and my NA, and you should be able to find it. The NA, the angle, this angle right here is 20. Okay. So you're going to have NA sine 20, and that is the distance. What is the distance of this component? Oh, I already gave you the answer, so never mind. Wanted to ask that. Plus NA, this time cosine 20. So let's ask this one. What is the difference of the distance between this component and point B? So first you got to think, which component is this? Is it vertical or horizontal component? And what is the distance between that and point B?
1.5 inches.
1.5. This one is this this distance that we're looking for, 1.5 inches. 1.5. The other distance was this one that we were looking for, 0.75. What else I have? I have EX. Minus EX, which I know the value. What is the distance between EX and point B?
1.75.
1.75. Okay. It's this one that I'm looking for, 1.75. Okay, you guys do the math and figure out NA. I don't know, well, I know how much it is. All I know it's that it should be larger than 5. So find NA on your own, do the math, okay? Questions? So I could have done a lot of extra work here, okay, which doesn't hurt. For example, here I could have had another equation, summation of y equals 0, and find EY, right? I could have used the upper handle equation if I wanted to draw free body diagram 3 and find BX and BY. I can totally do that. Then in this free body diagram number 2 that I have, all of the forces are known except NA. But they were extra. I wanted to be efficient and, you know, smart about it. So that's why I didn't do extra work. So if you really pause for like 5 seconds and look at your free body diagram, think about it before just writing equations, it can save you a lot of time and it's going to be more efficient. Questions? Okay, let's do another one. We can do this Monday. Let's do this one. Let's at least get the free body diagram done. Table AB supports a box that weighs this much. Apply the point G, find a vertical force that the operator must apply to keep table in equilibrium in the position shown. Find forces supported by all members of this machine. Okay, I was gonna ask you, what is this? Is it a frame? Is it a machine? Is it a truss? It kind of gives it away. It's a machine. The reason for it is why? Why is it a machine? Let's list the members here. I have AE. I have AGB or AB. And I have BCD. So let's look at them and you guys tell me if it's a 2-force member, 3-force member, multi-force member, you don't know. So let's look at it. AE. What is that one?
Isn't it a 2-force?
It is a 2-force, okay. Someone else said something too. Someone said 0-force.
I was also saying it's a 2-force.
Oh, 2-force, okay, good. One thing I should mention about 0-force, I don't know if someone said that or not, but 0-force members means you should be able to remove them without any changes in your truss. Okay, that's always a good test for you. See, hey, if I remove this, does that change anything? So going back to 0-force member, but yes, AE is a 2-force member. Why? Because all I see is a member, it's pinned at the end, and there's nothing pinned in the middle, there's no force in the middle. Everything that is applied to this member should be only at the ends. Okay, what about AB? That one is also only pinned at the ends. So is AB a 2-force member or a 3-force member?
3-force because it
Three-fourths
has
because
G.
point G, because G's pushing down on it, right?
Point, yes, point G. So yeah, if I didn't have point G, that would have been also a 2-force member, because the only pin at the end and there's only forces applied. But the problem tells me there's a 10-pound applied at point G. So there is a force here that the problem didn't put it on there, for me, but it's right there. So it's a 3-force member. What is BCD? What's a BCD?
Wouldn't it be a 3-force member since it's pinned in the middle?
So that one is also a 3-force member because it has a pin in the middle of it. Okay. So I have 2-force members, I have 3-force members. So this is a frame or it's a machine. I think it's a machine because the person is applying some force. It's going to transfer the load and kind of maybe lift that box. Okay. So now that I know it's a machine, I have to take it apart and draw FBD of each member. Okay. So let's see. This is going to be A, B. This is going to be EA. And this is going to be DB or DCB. Okay. So you guys remember, so 2-force member, we said they should be either in tension, right? Or compression. What about 2-force member? How should we draw free body diagram of a 3-force member? What is the condition for that? All you guys did an assignment on this.
They have to be parallel or go through the same point of action.
So forces on a 3-force member, they should be parallel, right? Or they should go through the line of action should intersect at some point. So you got to be mindful of that when doing 3-force members and 2-force members. Okay, so 2-force member, it's always easier for me to start with a 2-force member when I want to put forces on there. I'm going to put A, E over here. I'm going to put AE over here. And then I'm going to put AE over here. Okay. Then so this is done. My 2-force member is done. Is everyone clear why I put FAE on the top member the way I put it? Why is it opposite? I'm not talking about the direction, whether it's compression or tension. You can flip it, doesn't matter. But is everyone clear why they're opposite of each other? And they're both tension right now because they're going away from pin A in both of the FBDs. Okay. The next one I want to do is put the 10 pounds external force or active force on there. Now I have pin B that I have to draw the free body diagram. So now you have to draw it in a way, you have a BX and BY, but you can't just put it in any way you want. Although I keep telling you, for unknown forces, it doesn't matter, right? But now it matters because it's going to attach to something else, plus it's going to be a 3-force member. So which way would you put it to make this a 3-force member? Apparently these can be parallel. So we have to kind of manage so they at least go through the same point of action, right? Same. So it's one of them. So point B, wherever I put my forces, it should be in a way that the resultant force needs to go this way. Okay, so now I draw it and you guys tell me if it's correct or not. I like to put Bx here and By here. Is this good or is this not good?
Not good because the resultant force isn't directly going to hit the line of action of those.
So the resultant force in this case is going to be here, isn't it? This is my force B. Doesn't it go in line with my, go through the same point?
If it were to face that direction, wouldn't it end up causing a moment?
Well, I'm not analyzing that any right now. I'm just trying to draw a free body diagram. And question is this a correct 3-force member or no?
Yes, since they're all going through the same line of action.
That's what all I care about at this point. Yes, you are right. It might be this way. I don't know. See that? That's also correct. But what is not correct is, for example, if you have it, let's see if we can make it incorrect somehow. If I put my Bx here and I put my By going this way, see, this is not correct anymore. See that? Because the resultant force is going this way. See that? The line of action. So that's the only thing. It's either this one or this one. They're both correct, which I don't know. But all you have to do is be mindful that the direction you put result in a 3-force member. So let's see. Now that I know that, I have to make point B going this way, By going this way. I know that point D says the operator apply a vertical force. So the vertical force is going to be here. Okay, this is a 3-force member. Again, I got to be mindful. Line of action. Line of action. So wherever I put my forces in C, they're going to be ending up this way too, which I think if I go Cx this way, Cy this way, I'm good. Because the line of action is kind of here. It did. Let me fix it. So Cx, Cy, it's going to have a larger angle and then it will go through it. Okay. The angle is not really my concern at this point. It's just the direction of the force, Cx, Cy. You can flip these forces, Cx and Cy, in the other direction. So this is another alternate FBD, Bx, By, Cx, Cy. Okay. I flipped both Cx and Cy, but again, all of these are going through the same point. So that's something to be mindful. We all go back to your assignment from last week that, or 2 weeks ago, when you said, what is the importance of figuring out 3-force member and 2-force member? So this is your free body diagram. Start solving it over the weekend, but I'll complete it on Monday, okay? Don't forget to submit your activity 6. It's due tonight. I see there's still probably 15 people that have not submitted it, but 80 some people have done it, so I appreciate it. Okay, if there are any questions, I'd be happy to answer. If not, you guys are good to go. Have a good weekend. Bison playing tomorrow, so watch the game and all of that. Any questions from the class?
None in here.
Okay, all right.